Hi guys, what's up? In this video, we will deal with meteorology in a different manner. Meteorology seems to be an abstract subject, distant from our everyday lives, when in reality, we have a number of things going on in small scale in our homes, things that are of interest to the study of meteorology. This video proposes to make this study even more interesting. We will make use of a number of analogies that go on in our daily lives to make understanding this science easier, which is super interesting, super nice. You'll see, it'll be cool. Layers of the atmosphere. Guys, you'll see, meteorology starts by studying the air that encloses our planet. This air is divided, this atmosphere, into layers. This atmosphere is divided into several layers. We will speak just of three of them, which are the ones that really matter. The first layer, the most important, is where everything happens, where it rains, where there's cold, where there's hot, where there's storms, it rains. It's the first layer that involves us, which is called the troposphere. It's there that everything happens. Airplanes fly, balloons go up and down. This layer is approximately up to 20 kilometers of distance from the surface of the Earth. The second layer, above the troposphere, is called tropopause. It works like a type of a lid which prevents the gases, the air that we breathe, to go off into space. This layer is very narrow. It has approximately 5 kilometers. After the tropopause, there is the famous stratosphere we hear so much about, especially because of its connection to the ozone layer, that thin layer that filters UV radiation. The stratosphere is quite a bit thicker, reaching out to 80 kilometers. These are the three layers most important, let's say, that we've just seen. Now let's talk a little about the wind. Wind is the life of the atmosphere. It's the life that we can perceive that exists in the atmosphere. Let's make an analogy to make it easier to understand with the concept of winds. If we look at a river, we see that it is a flow of fluid, in this case water, running on the surface of the earth. This movement of the waters in relation to the land we call river. The wind is also a movement, is also a river, but a river made of air. The only difference between the river and the wind is the type of fluid. Instead of water, it's air. So the concept of wind basically is this: a mass of air, a part of the air, moving in relation to the ground. Now let's talk a little about what causes winds. What causes this movement? Why does a mass of air that was in one region decide to move from this region to another? Let's see what causes this. To make it more interesting for us to understand the cause of winds, let's talk about other phenomena which occur, living phenomena as well. For example, this camera in front of me, it has a life, it has operation, which exists thanks to electric energy. It is connected to a cable which has a positive and a negative pole, and this difference in polarity makes this motor of the camera work and generates, let's say, the life of the camera. The television in front of you there works in the same way. It is connected to an outlet where we have a positive and a negative pole, and this difference in polarity generates the life, the operation of the television in front of you. Our bodies work in a similar way. Life, in general, human life, life cells, are based in differences of potential. If we look into matter, if we stop and look exactly, if we go into the intimacy of the matter, we can see that there are protons and electrons. Electrons are negatively charged, while protons positively charged. This difference of polarity, let's say, promotes the movement, promotes the life. And in the case of winds, it's the same thing, exactly the same thing. But the poles, in the case of the winds, is a bit different. Let's understand this polarity that generates that causes wind. Let's understand this polarity. Before we go into polarity as such, which is the cause of the winds, let's talk about a meteorological concept called atmospheric pressure. This big word might seem a bit complicated, but it's quite simple to understand. It's the following. This mass of air that is above us, occupying these three layers of which we spoke about before, this air has weight. Just like I have weight here on the ground. If we take a scale and put it under our feet, this scale is going to register the pressure of our weight, the pressure of our mass. Pressure, atmospheric pressure, is nothing more than the weight of all the air above our heads. This is the concept of atmospheric pressure, high and low pressures. Let's understand a little about what high and low pressures are. This atmosphere that is above us, which has a weight that we call atmospheric pressure, often this weight varies, becoming heavier or lighter. If we compare this to a fat person that gets on a scale, there's going to be more pressure on the scale. This is going to show a higher pressure. A thin person will show a lower pressure. The air also will vary its weight, the mass of it. This weight will vary as a function of the temperature. When we are speaking about temperature, we are speaking about distance between molecules. For example, when the molecules are closer to each other, we say that the temperature is low, that the heat is small. When the molecules are vibrating more, the distance between them is larger, the temperature is higher, the heat is more. So, a mass of hot air, where the molecules are super agitated, that is, they are more distant from each other, because they are more distant, they will occupy more space. The same molecules will occupy more space. This means that the density of that mass is going to be lower. That is, the weight of that air, that heated air, as compared to colder air where the molecules are closer to each other, the weight of the heated air is lower than the colder air. So whenever we have a mass of hot air, as compared to a mass of colder air, meteorology calls this hot air of low pressure, whilst the air, cold air, where the molecules are closer to each other, more dense, vibrating less, this part of the air, this parcel of air, meteorology calls high pressure. And it is exactly the proximity of hot and cold airs, masses of hot air and masses of cold air, this proximity between the two, this closeness between the polarities hot and cold, will generate movement. It is exactly this movement that we called wind in the beginning, that's what we're trying to understand, that this movement is associated to this difference in temperatures, hot air and cold air. The next step, then, is for us to understand how air is heated or cooled. The first thing that we notice when we observe our planet receiving sunlight is that the poles, not coincidentally, they are much colder than the line of the equator. Why is there this difference? Sunlight, which comes from the sun, reaches the surface of the Earth at the equator much more directly than it does at the poles. What happens? The surface of the Earth at the poles has a lot less incidence of light and consequently heats up a lot less than the surface on the equator where the incidence of sunlight is high. So there we can notice what? That the air that is in contact with the poles will be much colder than the air in contact with the equator. In reality, it is not the light that heats directly the air. Sunlight heats the surface of the Earth, and the contact between the air and the surface of the Earth is what will heat up the air or cool the air. The contact is what is important. Therefore, the air that is in contact at the poles will be a lot colder than the air in contact with the equator. There we already have our polarity, which we talked about. Masses of cold air in contact with the poles, masses of hot air in contact with the equator. This is going to generate a movement. This is going to generate wind. This is going to generate a flow in the air from the poles towards the equator. The air is going to move from the poles in the direction of the equator. Speaking in general terms, that's how it happens. This movement also happens If we, for example, giving an example that is easier for us to perceive, when we are at the beach, why during the day, when the heat is more intense, we notice that the breeze is always blowing from the sea to the land, and in the evening it reverts. The breeze that was coming from the sea to the land stops in the evening and the flow is inverted. What's happening? Let's understand a bit why do we have this sea breeze from sea to land. When the sun is heating up the surface of the earth, there are parts of the surface of the earth that are comprised of water and other parts comprised of land. Sometimes there are forests, trees, in short. The surface, when it receives sunlight, it heats up in different ways. Water heats up a lot less than land. What happens then? The air that is on top of the sea, the oceans, is less heated than the air that is on top of the continents during the day. It is exactly this difference in temperatures between the air that is on top of the oceans to the difference of temperature for the air that is on top of the continents. This difference generates the sea breeze during the day, the wind. The wind blows, the air moves from the colder region to the warmer region close to the ground. This is a movement that is called by this difference in polarity. Another example of difference of polarity that we have, and that is very interesting and it happens practically every day in our own homes, is the following. Have you ever noticed that when you're taking a hot shower, and let's pretend that the box that we're using has those plastic curtains. Who has noticed that when the box is warm, that water vapor going up and all, the curtain of the box, if we notice, it begins to lean towards our legs. Sometimes it can even be annoying, that curtain continuously trying to rub against our legs. Why does this happen? It's the same thing. It's the same situation as the sea breeze. It's the same situation of the air moving from the poles to the equator. What's happening? Inside the box, the air is warmer than on the outside of the box. So I have a high pressure on the outside of the box and a low pressure on the inside of the box. There is a movement of the air from the outside of the box, close to the ground, to move towards the box. We have a wind in small scale, but it is wind, blowing close to the ground from the outside of the box to the inside of the box. These three situations that we've just seen are, we can notice that they happen in very different scales. In the poles to the equator, a gigantic scale, sea breeze in a medium scale, and the movement inside the bathroom in a very small scale. All these three scales, we had movements of the air, a wind, which happened exactly because there was a difference in polarity, a difference in temperature, high and low pressures. Sometimes it happens, guys, that this difference in polarity is very high. And what does this imply? It implies in a violent movement of this wind, a movement that is intense of the air. This is exactly what determines the intensity of the wind. Those days when the wind is blowing very hard, this means the following, that there is a high pressure and a low pressure. There are poles that are very different. There are temperatures between masses of air that are very different. The higher the difference between these temperatures, the faster will the movement be, the more intense will the movement be. So the intensity of this flow, the intensity of the wind, is related to this difference in polarity, and not only this difference in polarity, but I also need the proximity of the polarity. If I have high and low pressures close to each other, this intensity, this flow, this wind, will also tend to be more intense. Another aspect related to winds is the issue of the direction of the wind. So far we've only spoken of intensity, the issue of polarity. So why does it sometimes blow coming from the north and sometimes coming from the south, from the east, from the west? What determines the direction of the wind? Well, guys, it's not very difficult to explain. If I have a low pressure here and a high pressure here, we will see that the flow will be in this direction. So if I have a flow, in this case high pressure, low pressure, I have a flow from your right to the left. If I had, for example, a high pressure here and a low pressure here, I would have a flow coming from you to me. This way, from the way in which the high and low pressures are positioned, we can understand the direction of the wind. Simplifiedly speaking, it happens in this way. There are also other factors related to the direction of the winds, other forces that we will not mention so far here, because they are forces, they are laws that are more complex that rule the direction of the winds. But this vision, this position of the high and low pressures is already enough for us to understand why the wind is blowing from one direction to another direction. Now we will talk about other interesting aspects as well from the point of view of meteorology, which is also present in our day today, even if it doesn't seem to be. We'll speak of clouds. The clouds, guys, when we see them up there in the sky, printed against that blue backdrop, they seem to be so distant, so fantastic, nearly a fantasy we have when we look at clouds, you know, so distant from us. It's not necessarily in this way that clouds present themselves to us. We have in our homes, and we'll give a few examples for you to understand how interesting this is, we have the cloud phenomenon happening inside our homes. Inside our own homes, we have clouds happening, like they happen up in the sky. Let's understand a bit then, what is this phenomenon that we call clouds? The first step to understanding what a cloud is to perceive that water, like practically all the matter, occupies space in three different ways. It has three states: the gaseous, the liquid, and solid. The gaseous form, water is invisible. For example, between me and the camera, there is water, H2O, in gas state. And we call this vapor, and it is invisible. There's no way for us to see water when it's in this state. In the liquid form, we notice it visibly. It's easy to see water in liquid state, and in solid state too. Clouds are nothing more than part of the air where water was in gaseous state, and that for some reason, which we'll understand, decided to move into the liquid state. It became visible. So clouds, for the beginning of our conversation, are made up of water in liquid state. There was water in the vapor state, invisible, which for some reason became visible and became liquid. It is the white stuff in the clouds. That's the water that is in suspension in the air. So let's understand a bit better clouds by bringing this situation, cloud, to a phenomenon that happens in our everyday at home. For example, if we fill a glass of water at room temperature, if we fill this glass with water and leave it there in front of us, we will notice that after 1 or 2 hours, the glass is still there with water inside, and the walls, the outer walls of the glass, have suffered no changes. They continue dry. Now, if we take an ice cube and put it inside the water, we will notice that in very little time, the outer walls of the glass begin to get wet. They become damp. Some people even say the glass is sweating. Exactly what is going on there around the glass is the condensation. It is the formation of a cloud. A cloud is nothing more than the condensation, the change of state in water from gas to liquid. In the glass, the iced glass, the same thing happens. So we have at home, on top of the table, a reproduction of a small cloud happening right there. All we have to do is cool that water. Every time that we cool the vapor of water, every time that we have water in gaseous state, and this water is cooled, this cooling provokes the change in state of water from gas to liquid. It is those droplets that we can see forming on the outer walls of the glass. And this is nothing more than a cloud. Another example, typical, that we also have at home of forming clouds is that situation where we have a pan on the stove, pan with water there boiling, and as the water begins to evaporate, what happens? The water that was in liquid state in the pan, because of the heat, moved to the gaseous state. It became invisible, and immediately after the gas state, it became that smoke, that white smoke. That white smoke, which, contrary to what most people say, is not water vapor. That white smoke is a cloud. That white smoke is water in liquid state, and not water vapor. Vapor, as we've just seen, is invisible. So the pan that was boiling on the stove is an example in the home that reproduces the creation of a cloud. The vapor that was there condensed and became visible in that white smoke, and then where did it go? It went back to the invisible state. It went back to being a gas, which is exactly the same thing that happens in a cloud. The cloud is up there, it is formed, and we can see that whitish part. And where does this whitish thing go? It disappears. It evaporates. The cloud always is a process of condensation and at the same time evaporation. The water does not eternally remain transformed from gaseous into liquid. There is this return to the gaseous state when the cloud disappears before our very eyes. It is exactly going back to the gas state. In this photograph here, people, we can perceive quite clearly that there is a part of the sky that is blue and a part of the sky with clouds. What does this mean, interpreting meteorologically? That we have here, where we can see the clouds, water in liquid state, H2O liquid, and where there are no clouds, in the blue portion, water in gas state, invisible. Let's speak now about the types of clouds that there are. Meteorology classifies clouds according to their aspect, to their shape, and according to the altitudes, the heights at which these clouds were formed. According to the format, the clouds are classified basically into stratified clouds. The name itself already says stratified. Something that is stratified is something that is spread out without very defined shapes. On the other hand, there are those clouds that are formed that have shapes, contours well defined. These clouds with the shapes that are very well defined, well outlined, they are called cumuliform clouds of cumulative aspects. These cumulative aspect clouds, they receive the name of cumulus, generically speaking. Generically speaking, people, because many times the word cumulus is going to be a part of the remainder of the name of the cloud. We can have, for example, a cloud called stratocumulus. And this is a type of cloud where it is neither very much cumulated or stratified. It's a midway point between the stratified aspect and the cumulative aspect. The name of clouds are also associated to the altitude at which they are formed. So, for example, clouds that are formed closer to the ground, up to 2 kilometers from the surface, which are the stratus, the stratocumulus, and the cumulus in general. At an intermediate level, there is a second classification of clouds which receives a prefix alto before the name. So these are clouds that are not formed neither on the higher part of the atmosphere and nor down here close to the surface. These are intermediate altitude clouds. These clouds are generically called altocumulus, altostratus, the altostratus and altocumulus as a function exactly of the shape that they have. There is also a third class of clouds called cirrus, which is formed at the end of the troposphere, that first layer that we've spoken about previously. This cirrus is exactly clouds that are there hanging at around 10 to 12,000 meters, depending a bit on the latitude where we are. Cirrus are already a different class. They are comprised of small microscopic ice crystals, which are different clouds, because they form at an altitude where the temperature is minus 30 degrees, minus 40 degrees, sometimes minus 50 degrees. In spite of Cirrus being at that distance, at that altitude, we can also reproduce them in our homes. If we open the refrigerator and open the door to the freezer, we will see in there that inside the freezer, water did not go through the liquid state. It went directly from gas, which is a gas, which is H2O that went into the refrigerator, came into contact with that wall that is very cold of the freezer, and there it moved directly to the solid state. We call this sublimation, different from condensation. Condensation is when water goes from the gaseous state to the liquid state. In sublimation, it doesn't go through liquid state, it goes directly to solid. In the freezer, then, we have the ice crystals formed. These crystals, they are exactly or very similar to the crystals formed in the cirrus. Let's spend a bit more time with cumulus. The cumulus are those clouds that, when we are traveling on the road or even just looking out the window, they are those clouds that often have animal shapes. We like to associate, in particular children, like to associate these clouds, the cumulus, to animals, for elephant-shaped, dog-shaped, rabbit-shaped. So these are the cumulus. And when the cumulus become very large, they culminate, let's say, the maximum degree of evolution that cumulus reaches is called the cumulus nimbus. Meteorologically speaking, of course, the cumulonimbus, colloquially speaking now, is nothing more than a storm cloud. The cumulus, when it develops very much, when it reaches high altitudes, often the cumulus grows so much that it explodes so much upward that it exceeds the altitude of the cirrus. So sometimes they can exceed the limit of the troposphere and move into the tropopause. These are gigantic clouds with over 25 kilometers of altitude. They are called cumulus nimbus. These are those famous storms that flood cities. In short, all that disruption caused in traffic in cities, the flooding is caused especially by these clouds, the cumulus nimbus. So these are clouds that are associated to lightning, thunder. The cumulus nimbus is very interesting to be studied by meteorology because since it is a powerful manifestation of nature, it causes a lot of damage. So meteorology is very much concerned with the formation of this type of cloud. In relation to cumulus nimbus, there are some curious facts, interesting ones involving this type of cloud. For example, these storms, the scientists say that they were responsible for the origin of life in our planet. If it weren't for the electrical discharges that occur inside these clouds, the life in our planet would not be possible. Another interesting data that National Geographic raised is that there are 45,000 of these clouds, 45,000 CBs, cumulus nimbus are also called CBs, during the day. In a whole day, 45,000 manifestations of this size, powerful ones, like the case of cumulus nimbus, happens in the planet. Another interesting data item is that 1/3 of these electrical discharges generated by cumulus nimbus occur in Brazil. Another topic that is interesting for us to deal in this block of basic meteorology is the issue of fronts. Every so often we hear on TV that issue, there is a cold front coming from the south and the weather is going to change. What are fronts? Let's try to understand a bit this phenomenon called cold front. There are other types of fronts, the hot front, the Occlus front, but we're going to speak only of cold fronts which are easier and happen more frequently. The cold fronts are nothing more than the line of contact that exists between a high pressure, which we've already spoken about, and a low pressure. That's the line that divides a mass of cold air, a mass of polar air. We call them polar air masses because they come from the poles. So it is the dividing line between the mass of polar air and the mass of hot air. Between these masses of air, which displace from the poles towards the equator, is where we have the phenomenon called cold fronts happening. Let's do an analogy to make it easier to understand and visualize a cold front. This cold air that comes from the poles towards the equator comes in a shape like the front of a sports car, exactly with the front of a sports car, and that's where you have the name coming from, front. So the cold air comes like a wedge, raising the hot air, which is lighter, and causing, with this rise, clouds, a lot of nebulosity. And it is exactly this nebulosity, that we notice in the shape of rain. And this movement of cold air pushing the hot air upwards, generating these clouds, and many of these clouds are the classical cumulus nimbus that we've just spoken about, is exactly this movement, the presence of a cold front that generates nebulosity and consequently rain, and as soon as the cold front is done passing us, the temperature drops. Exactly because the mass of polar air, the mass of cold air that came from the poles, is now in contact with us. That's it, guys. So this is where I stop, and I'm leaving you with a different impression of meteorology. That was the objective, of demystifying a bit this distance of the meteorological science, bringing this a bit into our own homes, and hoping that you will be able to make use of this form of exposure that was used here, that you manage to use this in your day-to-day lives. We tried to make things in a different way, to develop this topic of meteorology in a different way, for it to become nicer, so that you, when you are in your everyday lives, in your homes, you might be able to notice that, that is also a meteorological phenomenon. Look how similar to a cloud it is. This is all very nice. When we bring closer these things that happen in our atmosphere, when we bring this closer to us, it seems that we become more intimate with the atmosphere.